Hi guys, and welcome to this, a video for MaffsGuru.com on the Specialist Maths course. We're dealing with the derivatives of inverse circular functions. Ka-ching! How exciting could this get? Well, nonetheless, if you haven't already done so, can you subscribe to my YouTube channel and head over to MaffsGuru.com and sign up, where it's absolutely free and you get these videos and downloadable notes and time codes and exam questions and so much more. And give us a shout out to your mates as well. They're the only people watching these videos are probably my mum and my current students, which isn't a bad thing. Hi guys, welcome to see you. Now, what are we dealing with? Of course, as I've said here, we've looked at trying to differentiate inverse trig functions. All right, inverse circular functions. If we had y equals sine to the minus 1 of x, how would I differentiate that? Well, strangely, the previous video gave us a bit of an insight into how to do that, because I know that that can become sine of y is equal to x, and now we can do dx by dy is equal to sine goes to cos of y, and as such then we know that dy by dx is 1 on the cosine of y. Now that might be useful to us if they've given us y values, but in many cases we want to know what x values are going to be substitutable in. So here's the question for you: how do we go from cos to something else? Well, let's have a look now. Let's find, now obviously in this situation I want to give you the formula. So when you have y equals sine to the minus 1 of x, the differential is given by 1 on the square root of 1 minus x squared for x values between minus 1 and 1. And again, remember why? Because when we look at the inverse sine function, what do we have? We have x values only between minus 1 and 1. And our y values go between minus pi on 2, if you remember, and pi on 2. So that gives us a framework or a reference for the values that are possible, but how do we go there? So what we just said was, we said that dy by dx was equal to 1 on cos y. And what formula have I seen that's got cos in it? Oh, hold on a moment. I know that sine squared of x plus cos squared of x is equal to 1. So I know that cos squared of x is 1 minus sine squared of x, and so cosine of x is equal to 1 on the square root of 1 minus sine squared of x. But we've got to do plus or minus. Now obviously in this situation here, why is this important to me? Because what I'm now going to say is the cosine of y thereby must be equal to the square root of 1 minus the sine squared of y. Well, how is that useful? I don't know. Well, hold on a moment, we knew that sine of y was equal to x, so sine squared y is equal to x squared. So we now know the cosine of y is equal to plus or minus 1 minus x squared. You see where that's come from on my formula? We're almost there, but we've got this problem here of a plus or minus. All right, so we know that our cos of y value, in fact, our y values fall between minus pi on 2 and pi on 2, yes? Is that inclusive? No, he says, just checking, yes? And we know that cosine of y has to be greater than 0 for those things there, yes? How do you know that? All stations to Canberra. So I did all stations to Canberra or Carrum Downs. There is minus pi on 2. There is pi on 2. If I look at those values there, cos is always positive in those functions. Yes, so cosine of y is always positive in those. So in which case, we're going to say that cosine of y is equal to the square root of 1 minus x squared, and therefore dy by dx is equal to 1 on the square root of 1 minus x squared. That's the proof. We'll show how to use it in just a moment. But in the same ways, we can also look at the derivatives of cos, yes? If we look at the derivatives of this, what do we notice? Well, here again is my final formula. F dash of x is equal to minus 1 on the square root of 1 minus x squared. How do we get that? Well, same really. So we now know that if we have y is equal to the cosine to the minus 1 of x, swap the cosine over to the other side, and then differentiate it. So dx by dy is equal to, well, cos goes to the minus sine of y. Oh, hold on a moment. So therefore, dy by dx is equal to minus 1 on sine y. See where we're going now? Oh, I should go. We're going to go back to the same idea. Well, we know that sine squared of y plus the cosine squared of y is equal to 1. So sine squared of y is 1 minus cos squared of y, or the sine of y is the square root, or positive negative, of 1 minus the cosine squared of y. But we already know that cosine squared of y, going back to this, would be x squared. So we know sine of y is equal to the positive or negative of 1 minus x squared. And we just have to try and work out which one it's going to be, the plus or the minus. Well, again, what do we know about our domain? It goes between 0 and pi. Yes, so it goes between 0 and pi. Let me just check that. Yep, 0 and pi inclusive. Let's make sure it's inclusive. And so what do we notice? Well, when I have my all stations to Canberra between 0 and pi, my sine values are all positive. So because sine y is always positive, we're going to choose the fact that sine y therefore is equal to the square root of 1 minus x squared. And so therefore, dy by dx is minus 1 on the square root of 1 minus x squared. Ka-ching. And guess what? We can do the same thing for tan. Yes, we can indeed do the same thing for tan. All right, so we know that tan is going to be defined vertically between the values of pi on 2 and minus pi on 2. Yep, so again, we know their values, minus pi on 2 and pi on 2. And so, same. Now we notice now, we know that tan of y is equal to x. So what is the differential? So dx by dy is equal to, well, tan goes to sec squared y, and so dy by dx is equal to 1 on sec squared y. Thank you very much. Now, how's that going to help us? What do we know sec squared is? Well, it's 1 plus tan squared. So we know that sec squared of y is 1 plus tan squared of y. Okay, so hold on a moment. This is nice and easy. We know that if tan y is x, then tan squared is 1 plus x squared, and we're actually done. So we know therefore that dy by dx is equal to 1 on 1 plus x squared. So those are them proven. My advice is to write it in your summary books because they're going to be really, really important. I know about you, chances of me remembering those are slim to zero in light of all the rest of the stuff we have to do as well. All right, so here are our general inverse circular functions now when we have fractional stuff. So we've chosen, we've looked at the 3 whereby it's just sine of x, cosine of x, and, or inverse sine of x. I'll try that one again. Sine to the minus 1 of x, cosine to the minus 1 of x, and tan to the minus 1 of x. What if we actually have a fractional component? Well, again, we can prove all this stuff. I'm really not going to go to that because it's going to take too long on the video. If I teach you, then we may go through it one lesson. But again, it's always an idea to make sure that you've got those written into your summary book. And again, what we notice is, for example, that sine to the minus 1 of x on a just gives you, if y is equal to that y dashed is equal to 1 on the square root of a squared minus x squared, right? So that's my general solution to allow me to do that. Those are going to come in handy. For example, now when we do some examples, so differentiate each of the following with respect to x. We'll start with the first one, sine to the minus 1 of x on 3. Well, we know that this inverse sine is given by, so we know that f dashed of x is equal to 1 on the square root of a squared minus x squared. Do I know the values of a? Yes, a is the bottom value, which is 3. So it's going to become 1 on the square root of 9 minus x squared. Ka-ching. Okay, this next one's a little bit trickier because we're now going to start to use the chain rule, absolutely. So we now know that if we've got y is equal to cosine to the minus 1 of 4x, yep, that's not easy to do because it doesn't fit any of our formulas. So what I'm now going to do is say that y dashed is equal to, if we let u equals 4x, then du by dx is equal to 4. And so this is going to become the differential of cos to the minus 1, okay, of 4x, which is going to be 1 on the square root of, well, in this situation, x, what's that going to be? U. So we've got, if you notice, that's now got a u there on 1. So that's 1 squared minus u squared. Yes, and I'm going to multiply that by the differential, which is 4. So that's going to give me 4 on the square root of 1 minus, well, whatever u squared was, we knew that was 4x squared, which is 16x squared. So there we go, 4 on the square root of 1 minus 16x squared. Same idea here, tan to the minus 1, let u equals 2x on 3. So du by dx, just using the chain rule, is going to give me 2/3. Rightio. So now we're going to now turn that into the tan of u, or tan to the minus 1 of u. We can do that. So we know that f dashed of x is equal to, well, tan we know was 1 on 1 plus x squared, in which in this case is u squared, but I'm going to have to multiply that by the differential of the bracket, which is 2/3. And so in which case that becomes 1 on 1 plus u squared, which is going to be 4x squared on 9 times 2/3. All right, so again, we're now having to do a bit of simplification. What is that going to be? So that's going to give me 1 on 9 plus 4x squared on 9 times 2/3. Reciprocate that gives me 9 on 9 plus 4x squared times 2 on 3, which gives me 18 on 3 lots of 9 plus 4x squared, and 3's go into there 6 times. So 6 on 9 plus 4x squared is my differential. And sorry about the messy working out there, but that took slightly longer than I imagined. But you see what we're doing each time? Yes, the chain rule is coming into this. So again, if we say that u is equal to x squared minus 1, du by dx is going to give me 2x. Happy with that so far? Awesome. So now we've got f dashed of x is going to give me the differential of, well, that's now going to become sine to the minus 1 of u. So we know that that's 1 on the square root. Is sine or is sine negative? Nope, that's it. 1 on, which means I may need to go back here and change that to a negative. There you go, guys. I noticed that should have been a negative because the differential of cosine. My apologies, yeah? At least I picked up on that one. Now, f dashed of x is 1 on a squared, which is 1 squared, minus, in this situation, u squared. We've already chosen u squared as x squared minus 1 squared, and I'm going to times that 2x. Now, realistically speaking, what I did here was bad mathematical notation, all right? And so I'm probably going to record these videos again, because I was always taught at school, if you have an x here, you can't mix those values. It's really bad mathematical practice, all right? So in this situation, I'm just showing you it again. So that's going to give me 2x on the square root of 1 minus x squared minus 1, all squared. We'll have to multiply that out to give me 2x on the square root of 1 minus x to the 4 minus 2x squared plus 1, which gives me 2x on the square root of 1 minus x to the 4 plus 2x squared minus 1. They're going to cancel, which is going to give me 2x on 2x squared minus x to the power of 4 square rooted. Now again, this is a bit of a trick and I'm running out of room, but what you notice is I can actually take out x squared out of that. So that's going to give me 2x, the square root of x squared times 2 minus x squared. And what do you notice about the square root of x squared? Be careful here. So the square root of x squared is actually the modulus of x. So in that situation, we get 2x on mod x times the square root of 2 minus x squared. So we've got to work out what happens there with possible solutions, because modulus of x can take two values. Yes, it can be plus x and it can be minus x. So that can be 2x on x root 2 minus x squared, well, in which case the x is to cancel. That's one of my differentials. And then the other one would be 2x divided by negative x root of 2 minus x squared, and again that would then be minus 2 on the square root of 2 minus x squared. And obviously in that situation you'd need to then work out, well, which of these would you use and when? And referring to my notes, it suggests that for the positive one here, you'd be looking at that being from 0 to x to the square root of 2, yes? And this one here would be for my values of negative root 2 to 0 x, sorry, that should be an x to 0, yes? And hopefully that makes sense to you. Thank you very much for watching. This is the end of this video, and hopefully you found it useful.